All right, hello chemistry class. Today we are doing a lab on chemical equations. And this is going to be a great lab not only to witness chemical equations or chemical reactions and then to talk about the chemical equations that go with those reactions, but it's just a nice review of a lot of concepts we've been talking about. So let's dive right in. The first thing that we often like to do is to talk about some of the key words that we're going to be using in this lab. So let's go ahead and define these very quickly. We have talked a lot about these definitions already and used them throughout the course. So an element, these are on the periodic table, right? On the periodic table, and they have a single type of element, or it's a single type of atom. All right, so as one type of atom has a unique number of protons, okay, with atomic number. Remember, that's the number of protons. So every element has its own unique number of protons. A compound is two or more elements bonded together. An atom, those are the basic building blocks of all matter, and we can just put basic building blocks. Remember, an atom, you've got your nucleus, you've got your protons and neutrons in the nucleus, and then you've got your electrons outside of that nucleus. Okay? Molecules and compounds are very similar. Here you've got two or more elements. Molecule is basically saying you got two or more atoms. And the reason we distinguish that is you can have two of the same atoms bonded together. Like you can have O2, there's an oxygen and an oxygen bonded together. That's a molecule, but it's not a compound because the atoms are the same here. The element is the same. Okay. Chemical formula, we use that to describes elements and quantity of those elements in a compound or in a molecule. Okay? Valence, those valence electrons, these are the outermost electrons. A chemical reaction. Chemical reaction is when new product is formed. And we're going to see some of the chemical reactions today. Law of conservation of mass basically is saying mass before the reaction must equal mass after. You cannot create or destroy matter. Our chemical equation is going to describe the reaction. All right, it's going to have balanced number of atoms of each element, and it's going to show the reactants on one side and the products on the other side. Okay? The subscript is telling us the number of atoms, I should say, of each element in a compound or in a molecule. Okay? The coefficient number is telling us the number of molecules, or let's say compounds. Number of compounds or molecules, number of compounds or molecules in the reaction. And remember, that can represent number of compounds or molecules. It also can represent the number of moles of those compounds or molecules. Precipitate is solid formed from aqueous solutions mixed. Reactants, those are before the reaction. Those are the compounds, molecules that you have before the reaction. Products are after. Okay. Balanced equation, this is using coefficients. Okay, you're going to basically conserve mass. By using coefficients. Okay. A few more here. A single replacement reaction. An element replaces another. One element. Okay, one element replaces another that was in the compound. Double displacement or double replacement is there's a switch of elements in the two compounds. Okay. Decomposition is breaking apart. And synthesis is combining. A catalyst is basically a substance that speeds up the reaction. Okay? Speeds up the reaction, but it's not consumed. It's not part of the products. It's not used. These are some different symbols that we use in writing a chemical equation. This just means aqueous, solid, liquid. So you'll see these symbols next to the formula. Gas. This also can mean that a gas was produced. This is mean that there's heat involved. That delta symbol is a change in heat, change in probably temperature. Down arrow would also mean there's a solid, or we could say precipitate. And then this means yields. That is going from reactant to product side. Okay? All right. A few more things here to make sure that we know how to write these chemical equations correctly. We are simply just going to write the symbol and then the ion that is charged, that is formed when that particular element gains or loses electrons. So this is really simple because all you have to do is you have to look at the periodic table. If you look at the periodic table, we should remember that everything in group 1 here likes to lose their one valence electron, so they're going to form +1 ions. Everything in group 2 is going to lose the 2 outermost valence electrons, so it's going to form +2. We're going to skip over these transition elements because they vary. And then here, group 13, they have 3 valence electrons, so they have to lose those 3. Group 14, they prefer to share, so we're just going to skip that. But if they do, they actually could do +4 or -4 probably, because they have 4 valence electrons. Now we get into group 15. Group 15 has 5 valence electrons, so it's easier just to gain 3 to get the octet. So it's going to gain 3 more, giving it a -3 charge. Oxygen is in group 16, has 6 valence electrons. It's going to gain 2 more to get 8. Remember, they always want to get that octet. They want to get 8 in the outer energy level. So oxygen is going to gain 2 more to get 8, so it's going to be 2 extra electrons, a -2. Fluorine and the halogen group here, group 17, have 7 valence electrons. It wants to gain one more to get a negative 1 charge on the ions. And then the noble gases, they are full already. They don't want to gain or lose. They are not very active. They don't like to react. They don't need to combine with others in order to get their octet. Okay? So all you have to do is look at the periodic table. That's it. Just look at the periodic table and you know exactly what their charge is going to be depending on what group they're in because of the number of valence electrons they have, how much do they want to gain. All these metals over here, these metals, they want to lose electrons. They like to lose those outer valence electrons, and then the outer energy level will be below that and it'll be full. And then these are their nonmetals here. Your nonmetals like to gain. They like to get a few more to complete their outer energy level. And then you can see that's a perfect match. Metals lose electrons, nonmetals gain electrons, and so they pair up in a correct ratio so that everybody is getting the number that they either want to lose or gain and form a neutral compound. So all we have to do is just look at this and we can determine exactly how many they want to gain or lose and what the charge would be. So hydrogen, all we're going to do is write the symbol, and I'm going to make a middle column here when it becomes an ion. I'll put it at the end here. Hydrogen is in group 1, so it's going to lose that outer electron. Okay, it's going to form a +1 charge like that. That's how I'm going to do it. Chlorine, it has 7 and wants to pick up one more, so it's going to have a -1 charge. Zinc, if you look here, now zinc is in the transition elements, but it's fairly consistent. I believe zinc is a +1 if I'm not mistaken. Okay. Sorry, I made a mistake here. Zinc actually is a +2. Alright, so it's one of those transition elements that does not change its ion charge. So it's a +2. Sorry about that. Now, if you see a Roman numeral here, it's telling you the charge, because copper could be either 1 or 2. So the symbol for copper is always Cu, but if it becomes an ion with a +1 charge, it can be copper 1. If it has a +2 charge, it's +2. Same thing with iron. The symbol for iron is always Fe, but if it loses 2 of its outer electrons, it becomes a +2 ion. If it becomes +3, it has lost 3 of its outer electrons. Silver is always a +1, pretty sure about that one. And then here you got mercury 1 and 2, same thing. Mercury is always Hg, but when it loses 1, or it can lose 2. Okay. Potassium, again, all you have to do is look at the periodic table. You'll see that potassium is in group 1. Really simple. So potassium likes to lose that outer electron and become a +1 ion. Sodium, same thing with sodium. Calcium is in group 2. Magnesium is in group 2. Bromine is in halogen, so bromine likes to pick up 1 extra to fill that octet, to fill the outer electron shell, because it has 7, so it wants to pick up 1 more, -1. Oxygen would like to pick up 2 more. Oops, sorry, this would be a -1. Sorry, -2. Okay. Aluminum, let's see where aluminum is. Just check your periodic table. It's right here in group 13. So it has 3 valence electrons that it would like to get rid of. It's going to become a +3. Iodine is another halogen. Lead 2, it's telling you right here. So Pb is the formula for lead. If it gets rid of those 2 valence electrons, it's going to be +2. Barium. Barium is in, where'd you go, barium? Here we go, yep. Is in group 2, down there near the bottom. So it likes to get rid of those 2 valence electrons. Gold. Now gold is pretty stable. It doesn't like to react. It's pretty pure by itself. But if it did, I believe, I need to check on this here. All right. Well, actually, according to periodic table, it could be a +1 or +3. So we're going to go with +3 here, okay? Nitrogen, if you look where nitrogen is here, it's in group 15, so it wants to get 3 more to add to those already 5. So nitrogen picks up 3 more, it's going to be a -3 charge. 3 more electrons, okay? All right. Now, these these polyatomic ions I give to you. So the periodic table that I give to you, if you look on the second page or the back side, they're right here. They're all right here. So these are simply groups of nonmetals that are bonded together, but they have either more total protons than electrons or more total electrons than protons. So they're going to have a charge on them, okay? And you can see the groups are here and the charges are written as superscripts there, and the names are all given to you, okay? So let's just go ahead and fill in some of these so you're familiar with them. Sulfate is SO4, and it does have a charge on it. It has a 2 negative charge. Nitrate is NO3, and it has a charge of also -2. And again, they're all right here for you. There's sulfate, okay? There's nitrate. Oh, I'm sorry, it has a -1. My fault. -1, I should have known that. -1 charge. Apologize. Okay. Hydroxide, OH, and negative has a -1 charge. Ammonium is actually one of those that is going to be positive. It's NH4 has a positive charge. Chromate right here is CrO4, and it has a -2 charge. Carbonate is CO3. It also has a 2 negative charge. Acetate, so one a little harder to remember, CH3COO. Sometimes it's written like that. Sometimes the O's are combined and the C's are combined, but we'll go with this here. -1. And then the chlorate is right here. Has a ClO3 with a -1 charge. Okay, so just use those as needed. Now, to combine these and form compounds, we are going to combine them in the correct ratio so that we get a neutral compound. All right, so we talked about all the charges up here. Some are positive, some are negative. We have to then combine them so that we get a neutral compound. So zinc, I'm going to show you the ions first and then we'll write the equation. Zinc is a 2+, chloride is a -1. All you do is you just take the number from the other one and that becomes a subscript for the element. So you're going to need 2 chloride ions to match the 1 zinc. So this is going to be ZnCl2, and this is called zinc chloride. Remember, we changed the name of the second one to end with IDE. Copper 2, so that's 2+, and hydroxide is OH negative. You're going to need 2 hydroxides, 1 copper. Copper hydroxide, like that. Okay. Silver and bromide. Silver is a +1. Bromide is a -1. Perfect, one of each. Silver bromide. Okay. Lead 2 and nitrate. Lead 2, it's telling you it's going to be a +2, and the nitrate, NO3 is a -1. You're going to need 2 nitrates, 1 lead. And this is lead nitrate. When it's a polyatomic ion, you just use the name as it is given. Hydrogen +1, chlorine -1. This is going to be HCl. This is, you could say it's hydrogen chloride, but when this is aqueous, it's actually hydrochloric acid. So we're just going to put that down. We didn't name acids, so you don't have to worry about that. Sodium and hydroxide. So sodium is Na+, hydroxide is -1. So this is just going to be one of each. Sodium hydroxide, NaOH. Potassium, the +1. Chromate. Chromate was that Cr4 2 negative. Okay, so you're going to need 1 of the chromates, 2 of the potassiums. Just like that. And this is potassium chromate. Okay, calcium +2, carbonate is a -2, so you just need 1 of each of those. This is calcium carbonate, sorry. Aluminum is a +3, oxygen is a -2. So you need 3 oxygens, 2 aluminums. And this is aluminum oxide. Ammonium is the NH4 plus, and hydroxide is the OH negative. So there's just 1 of each of these. This is ammonium hydroxide. Okay. Barium is a +2. Chlorine is a -1. You're going to need 2 chlorides, 1 barium. This is barium chloride. Okay. Just a few more here. Zinc +2. Sulfate is a -2. So this is zinc sulfate. Calcium +2, hydroxide -1. You're going to need 2 hydroxides. This is calcium hydroxide. Potassium +1, chlorate, I believe was a -1 if I'm not mistaken. Chlorate, yep, -1, ClO3. So we just need 1 of each of these. There's the formula, and this is potassium chlorate. Iron 3 and hydroxide. Iron 3, you're going to need 3 hydroxides to match that 1 iron. So this is Fe, and then in parentheses put OH with a subscript of 3. Iron 3 hydroxide. Remember, when there are multiple charge options, you got to put the Roman numeral to tell me which ion you're using there. Okay. Silver is a +1. Acetate is a -1, so you just need 1 of each of those. Oops, so no charge, no charge. It's neutral now. And this is silver acetate. Iron 3, it's telling me exactly which one I'm using. 3+, and oxygen is a 2 negative, so I'm going to need 3 oxygens, 2 irons. Iron 3 oxide. Aluminum +3, and chlorine, so -1, so you need 3 chloride ions. Aluminum chloride. Copper 2, they're telling us that we're going to use the 2+ ion, and sulfate is SO4 with -2, just need one of each of those. So they're in a 2-to-2 ratio, okay, 2 of each, or you always reduce it. So you're not going to have a 2 on each of those, you'd reduce it to 1-to-1. So copper sulfate. Actually, copper 2 sulfate. Okay, magnesium is a +2, oxygen is a -2. So just need one of each of those in the same ratio here, 2-to-2 or 1-to-1, always reduce it. So magnesium oxide, and the name is magnesium oxide. Okay? Okay, so if we were to do these reactions, if we we're going to do these in the lab, what we're going to do is we're going to take the aluminum chloride solution and we're going to mix that with ammonium hydroxide solution. So let's just, if you were seeing these in the labs, this is what they would look like. This one, aluminum chloride, basically is a clear liquid, a clear solution. Okay, it's colorless, it's clear. The ammonium hydroxide is also clear, a clear solution. This one has a bit of an odor to it, if you were to get a whiff of it in the lab. The aluminum hydroxide is a white precipitate. It's a white crystal, I'll say that. So if this is going to be one of our products, it's going to be a white precipitate. And then the ammonium chloride here, ammonium chloride is still soluble in water, so that is still going to be a clear liquid, a clear liquid here. Okay, and this will make more sense as we proceed and represent this reaction with these two here, the two solutions being our reactants, and then these are our possible products. And you'll see that below as we work this out. For part B of this lab, we have a copper sulfate solution, and this one is more of a bluish, this is a blue solution. The sodium hydroxide is a clear solution. So again, these reactions are taking two solutions. We mix two solutions, and we're actually going to get a solid, as you're going to see up here. And here, this one, this copper hydroxide is going to be our blue precipitate, a blue solid. All right? And then this sodium sulfate is going to be still I guess it's going to be kind of a bluish liquid here, but this one is the precipitate, the copper hydroxide. So we're going to see that in the lab. All right. So these are, in part A, the reactants, as I mentioned, are the aluminum chloride and the ammonium hydroxide. The aluminum chloride and the ammonium, ammonium hydroxide. And for part B, the reactants are going to be the copper sulfate and the sodium hydroxide. Okay, so in a little bit we're going to see these reactants. This is the reactants for part B, these are the reactants for part A, and then the products for part A are going to be, and you'll notice what we're doing is we're just switching. The aluminum is going to go with the hydroxide to make aluminum hydroxide, and the ammonium is going to go with the chloride to make the ammonium chloride. So our products are going to be the aluminum hydroxide, that's for part A, and then the ammonium chloride. And this is the one that we're going to see. This is the precipitate there. That's going to be our white crystals. For part B, these reactants are going to produce the copper hydroxide. This is copper 2 hydroxide. So it's going to have OH2 there, and the sodium sulfate is going to be our Na2SO4. And this is the precipitate. Okay? So this is what it's playing out to look like. Let's go ahead and come down here and balance this, and we'll go back up and answer the remaining of those questions. Here we have Al, that should be an L there, and that's an LCl, AlCl3, This is our one solution. I'm going to put AQ there. With ammonium hydroxide, that's AQ. We mix these two solutions and we're going to see a double displacement, which means the first part of these two compounds are basically going to switch places. The aluminum is going to go with the hydroxide. And we have aluminum hydroxide here, and the ammonium is going to go with the chloride to produce ammonium chloride. Those are the correct formulas for everything. And then we have to balance this. We have one Al on both sides, so that's good. But we have 3 Cl's on this reactant side. We need 3 on this side. So I'm going to put a 3 coefficient in front of all that. That triples the number of ammoniums, so I got to put a 3 in front of this. That triples the number of hydroxides, which I do have 3 on that side. So now it is balanced. Let's do this one. Copper sulfate solution with sodium hydroxide solution. They're going to switch places, the sodium and the copper. Okay, and you're going to have copper hydroxide. That's the correct formula for copper hydroxide, and sodium sulfate. That's the correct formula for that one. And if we balance this, I have 1 copper on both sides. I have a sulfate on both sides, SO4. But here I have 2 sodiums, so this has got to be doubled. And then you'll notice that doubles the hydroxides, which I have 2 on that side. So everything is balanced. Okay? So these are going to be double displacement. That's what we call these, double displacement or double replacement. And that is basically where you have a switch. You're going to switch the cations. This is the cation, the first part of each compound. You're going to switch the cations to make your new products. Okay? And indications that a chemical change took place, well, most likely we're going to see a precipitate and or a color change. Those are possibilities there. Okay? Same thing here, precipitate, color change. Those are some ideas that you would be looking for, indications that a chemical reaction is taking place. All right? So let's just practice a few. We're not going to do all of these, but let's just practice a few of these double displacement reactions here. We'll just do 3 of them. That's all we have to do. And then we'll get back to what these reactions are going to look like. So magnesium sulfate and ammonium hydroxide, the cations are going to switch places. The first part of each of these compounds are going to switch places here. So we're going to make magnesium hydroxide. Well, magnesium is a +2, so we're going to need 2 hydroxides, which is a -1. That's the correct formula for magnesium hydroxide. And then the ammonium is a +1. The sulfate here is a -2, so I'm going to need 2 ammoniums for the ammonium sulfate. Now I need to balance this. So you'll notice that I need 2 hydroxides on both sides. I have 2 here, I need 2 there, so I have to double that. That doubles the ammonium, which I have 2 on that side, so everything is good. Let's go ahead and do this one. This is calcium and the sodium are going to switch places. The sodium is going to go with the hydroxide. Well, sodium is a +1 ion, hydroxide is a -1 polyatomic ion. You just need 1 of each of those. And then the calcium and the carbonate, calcium is a +2, carbonate is a -2, so 1 of each of those to make the correct formula. And then all we do is balance this. I need 2 sodiums on both sides, so I have to double that. And that doubles the hydroxide, which I have 2 on the reactant side, so we're good. Actually, this one's a little easier, so I'm not going to do this one. Let's go ahead and do... Let's do this one down here. This one's a little more interesting. That should be an Al right there. Aluminum hydroxide, and this is sulfuric acid, H2SO4. Again, the cations are going to switch places. So the aluminum and the hydroxide, or the hydrogen, are going to switch places. So the aluminum with the sulfate, aluminum is a +3, sulfate is a -2. So you're going to need 2 aluminums and 3 sulfates. That's the correct formula for that. And then the H and the OH come together to make water. And I'm going to write it as H2O, but to balance it a little more easily, I'm going to think of it as HOH. Okay? So you'll notice we have aluminum here. We have 1 aluminum and 2 on this side. So I'm going to put a 2 in front of that compound. That is going to double the 3 hydroxides. So I have 6 hydroxides there, so I'm going to put a 6 in front of the water to make 6 hydroxides. That is going to give me 6 hydrogens. I only have 2 on this side, so I'm going to have to triple that, and that triples the sulfates, which I do have 3 on the other side. So it is correctly balanced. Okay? Okay, let's look at, we're only going to write the names of a few of these. Let's just write the names of A and C. So this is magnesium. I'm just going to say it. I'm just going to say it if it's okay. We're going to save a little time here. We're just going to say the names and you can write it down for A and C. All right? So this is magnesium sulfate and 2 moles of ammonium hydroxide produce or yield magnesium hydroxide and ammonium sulfate. And then here for C, this is calcium hydroxide and sodium carbonate are going to produce 2 moles of sodium hydroxide and 1 mole of the calcium carbonate. Okay? So we just have to get used to saying the names in addition to writing the formulas. So that's enough for that one there. Okay? All right, let's get into talking about single replacement reactions now. So in the lab, we would be witnessing some single replacement reactions, and I'm going to show you hopefully a couple videos here that demonstrate these. Actually, let me go back and show you the videos of the double displacement reactions here, okay? So I'll show you a couple double displacement reactions here. These are actually not the ones that we're doing in this lab, but you get the idea by watching these reactions all the same. So I just want you to understand what a double displacement is. Here we have sodium iodide. And sodium iodide is somewhat of a clear yellowish solution. And then we're going to add lead nitrate. Lead nitrate here is it's also clear, but it's going to produce a yellow precipitate. That yellow precipitate is the lead iodide. And so you'll see what happened is the sodium and the lead are switching places. Now the lead is going with the iodide to produce this precipitate, lead iodide. And the sodium is going with the nitrate, but the sodium nitrate is still dissolved in water. That's why it says AQ. But that yellow precipitate right there is a solid. You could filter it out and it would be a solid. This is a double displacement reaction. Not the one that we just did in the lab in the handout, but it still is a double displacement, so you can see what's happening. Often in a double displacement, the neat thing about a double displacement is that when you form a precipitate, that's solid, then you can see something being performed there, okay, and being created. Let's go to another one here. This one is with copper. The bluish solution usually is going to be a copper one. So this is your copper sulfate. Again, not the one that we did. Oh, we did do copper sulfate in our lab. So copper sulfate is the blue solution. And then we're going to add to it here another solution. And that solution is going to be our sodium hydroxide. This is the one. This is part B that we did in the lab. Okay? And when we combine those two solutions, we start to put a little bit into put them together. You're going to see a blue precipitate. That cloudiness right there is actually a solid that is being formed by combining those two liquids. So here is your copper. Oops, sorry. Here is your copper hydroxide right here. All right, the copper hydroxide is the solid. It's the blue solid, the copper hydroxide, and the sodium sulfate is still dissolved in water. But again, how do we get that? We switch this copper and the sodium. We switch them. The copper now can go with the hydroxide. This is an insoluble solid that is going to be your blue precipitate. Okay? So those are examples of double displacement reactions that we would actually perform in the lab if you were doing this. Okay? Okay, now we can talk about our single replacement reactions. Our single replacement reactions are going to involve a solution, and then a single element. This is a single replacement. So let's talk about our part A reaction here. In part A, we're going to have a solution called copper sulfate, and we're going to introduce the metal zinc to it. Metal zinc is going to be your single element that we're going to introduce there, and we're going to see what happens as a result. Okay? Copper sulfate, let's write the formula for those. Copper CuSO4, and then zinc is just Zn, okay? And then copper is going to be our product. Copper is going to be the lone element by itself in the product side, and we're going to form zinc sulfate, okay? And we'll look at the reaction of that in just a second. But you'll notice this time it's just a single element on the reactant side, and that's going to replace the copper in the compound, and then on the product side we're going to have the copper by itself, and the zinc is going to be in the compound. For part B of this, we have hydrochloric acid, that's HCl, and then zinc is Zn, and we're going to form hydrogen. This H is going to come out because the zinc is going to kick it out. Hydrogen is H2, and then zinc chloride is ZnCl2. Okay? So, what indicated that a chemical reaction took place when zinc and copper sulfate were combined? You're going to see, in this case, a new metal. You're going to see the copper produced, which is going to be a bit of a, you're going to have that copper metal. The copper forms on the zinc. It's going to start taking the place of the zinc, okay, as you'll see in a little bit. And here, for part B, you're going to see bubbles, because what is produced here is the hydrogen gas. The hydrogen gases start to form and form the bubbles, okay? So what are the reactants in part A? In part A, we're going to have copper sulfate and zinc. Copper sulfate and zinc. And that is going to produce then, this zinc is going to kick out the copper, and it's going to be the copper that's by itself, and we're going to have the zinc sulfate in solution. And the copper is going to be formed by itself. So the zinc was the solid, we put that in the copper sulfate solution, then the zinc goes and starts to form the compound in the solution, and the copper starts to form the solid, as I'll show you. For part B, it is the HCl and the zinc. So the HCl and the zinc is by itself. Now the zinc is going to singly, it's a single atom, a single element that's going to kick out the hydrogen. And this is going to make then the zinc chloride, and this is still dissolved in water, but then the hydrogen comes out and you start to see those bubbles. Okay? So in part A, what was created? The copper. We started to form copper metal. And for part B, we started to form the hydrogen gas. Okay? I should say these are elements. Okay, yeah, those are the elements. And then the compounds, the new compounds in A were the zinc sulfate. But actually it's still dissolved in water, so there's still going to be ions, but that's okay. And then for B, it was the zinc chloride. Okay? All right, and for part B, what I would do in the lab is to show you there's actually hydrogen gas that is being formed. We would bring a flame to that, and we would see it, a bit of a flame produced because the hydrogen would burn. Okay, the hydrogen would burn, and we would show that there is hydrogen. We might get a little bit of a pop. Okay, flame to show that the hydrogen is being produced in that test tube. We get a bit of a pop from the hydrogen burning if I brought in a flame there. Okay, so let's go ahead and work this out. Here, this is the part A, single displacement. The zinc is put into a copper sulfate solution. It kicks the copper out. The zinc now is going to form your zinc sulfates compound, but that's still aqueous, it's still dissolved in water, and the copper now is by itself, and this is your new solid. And this is actually balanced already. It's fine. The zinc here, when you put in the hydrochloric acid, kicks out the hydrogen. The hydrogen is going to get kicked out. Hydrogen is diatomic, so it's always H2 in nature. And then the zinc goes with the chloride. That's the correct formula for zinc chloride. We have to balance this. Notice I have 2 chloride ions, so I have to double this, and that gives me 2 hydrogens on both sides, and we're good. So a single replacement reaction is simply when an element replaces another element in the compound. Okay? Single displacement, a single element is going to replace it. All right? So that is basically what you need to understand for this lab are the single displacements and the double displacements. Okay?
And let's wrap this up here by looking at a few more reactions on these single displacement reactions here. All right, we're not going to do all of these. Let me first of all show you these single replacement reactions, a little video here, and so you can kind of witness these. So this is a copper solution. The blue is the copper solution there, the blue liquid, and then you have a piece of zinc, and that piece of zinc is going to be inserted into the copper solution. And when that happens, the zinc is going to go into the solution as ions, and the copper that's in the solution is going to start to form, and it's going to be coated on the zinc metal, and it's going to look black. Okay, I know copper is not black, but there is what's forming. The form, it's sped up, but that is what's forming. Those crystals are copper, pieces of copper metal that are forming, and the zinc metal is going into the solution. To the copper sulfate solution. There's a before and after picture right there. Okay, before it was just all zinc, and the zinc then is going to go into the solution. It's going to change from metal into metal ions, and the copper ions that are in solution are going to start to turn into copper metal and be coated on that piece of zinc metal there. Okay, so there's a definite change, a replacement. The zinc and the copper are switching places. And you'll also notice that the solution goes from blue to nearly clear because it is the copper sulfate that's blue, but zinc sulfate is clear. So this solution is becoming zinc sulfate on the right side. Over here is copper sulfate. And that black crystal there, those are copper atoms. Okay? All right, let's see if we can find one for our other reaction so you can see some bubbles here. Okay, so for this reaction here, we're going to take some concentrated hydrochloric acid, and that's what's in the test tube right there. And then what we're going to do is we're going to introduce a piece of zinc, zinc metal. Now if you remember what the reaction is going to be is the hydrochloric acid has HCl. So the H is the hydrogen. But right now, it's HCl is hydrochloric acid. It's the HCl dissolved in water. Now we're going to put in a piece of zinc metal, and you'll notice that there are bubbles that are formed. Those bubbles are the hydrogen that's being released, because the zinc is going to take the place of the hydrogen, as you can see from this formula. The zinc here is going to kick out the hydrogen, and now the new compound is zinc chloride. That's going to be your solution, aqueous, AQ, and the hydrogen is getting kicked out, so it is normally a gas at room temperature, so it's going to just turn into a gas. You're going to see the bubbles. We're going to try to capture that hydrogen to show that it truly is hydrogen. So as we see all those bubbles produced, we want to verify that those bubbles that are being produced are hydrogen. So we capture it in that test tube above, and then what we're going to do is we're going to introduce a flame to what we think is hydrogen and see if it does react, see if it kind of gives us a little pop, see if that, that hydrogen that we captured actually is flammable. Okay? So all we do is we take away the test tube that was where the reaction was taking place, and now we have the hydrogen trapped here in this test tube. And we're just going to bring in a does actually produce a bit of a pop or a bit of a burn due to the hydrogen that was captured right here. Okay? And there it was. There was a little pop there. Didn't hear it obviously, but you can see there was a little pop there, and that's because that hydrogen that was trapped, that was escaping, trapped in that test tube, burned, and that's an indication that it was indeed hydrogen that was trapped there. Okay? All right, so let's do a few more of these single replacement reactions, and then we are going to be done with this lab. All right? So just a few more practice ones here. Here we have a single replacement. How do I know it's single? Because it's a single element that is going to react with a compound and kick that out. And these are probably all AQ, and these are probably all solids for the most part. So the Fe is going to kick out the iron. If it does, if it is one of them has to be more reactive, and if the iron is more reactive than the copper, then it will kick it out. So let's assume that it is, and it's going to kick out the copper, so we know copper is going to be all by itself, and then we just have to figure out what the new formula is. Well, iron, there can be an iron 2, so let's assume it's iron 2. So iron 2 with the sulfate, which is a 2 negative, and that's basically what we're going to get. And iron 2, we're going to assume that that is still dissolved in water, just like that. Okay? The copper, let's say this is, let's go with this one. Let's go C. Zinc is going to kick out the silver. Silver is going to be by itself now, Ag. That's going to be a solid. And then this zinc and the nitrate. Now the formula for zinc nitrate is zinc is a +2 and nitrate is a -1. So I'm going to need 2 nitrates to get the correct formula here. And then I have to balance this. So I have 2 nitrates. I need 2 on this side, put a 2 there. That makes 2 silvers, so I have to double my silvers as well. That's the balanced equation. Single displacement, single displacement. Okay? Let's do one where there maybe is a gas produced. Here this is water, but remember water can be written as HOH. So I'm going to write it as HOH because this calcium is going to kick out the hydrogen here. So that calcium is going to kick out the hydrogen. Remember, hydrogen is always diatomic when it's by itself. This calcium is going to kick out the hydrogen and combine with the hydroxide. So you're going to get calcium hydroxide. Now, calcium is a +2, hydroxide is a -1. So I'm going to need 2 hydroxides for calcium hydroxide. Now I need to balance this. To balance this, I'm going to have to put a 2 in front of my water so that I get 2 hydrogens, like on the product side, and 2 hydroxides, like I have on the product side. Okay? All right, let's do one more. In this case, what we're going to do is, this is a non-metal, and it only can kick out other non-metals. So the non-metal is the second part in this ionic compound. So the chlorine is going to kick out the bromine, and it's going to be the bromine by itself. It is also diatomic. The chlorine and the magnesium is a +2, chlorine is a -1, so it's going to be Cl2 like that, and it's balanced, just like that. All right? Let's do one more. Sorry, one more, okay? Here we have iron 3 oxide. Iron 3 oxide, the aluminum is going to kick out the iron in this case, and now iron is going to be by itself. Okay? And the aluminum oxide, I need to make the correct formula for aluminum oxide. Aluminum is a +3, oxygen is a -2. So we're going to have Al2O3, just like that. Okay? And everything, I need to balance, I need to put a 2 here, so I have 2 aluminums on both sides, and I need to put a 2 there, so I have 2 irons on both sides. And we have 3 oxygens on both sides. And there you go. All right? So let's just name the few that we did. This is iron, solid iron with copper sulfate solution, producing iron 2 sulfate and copper solid. And here we have silver nitrate and zinc, producing silver nitrate, aqueous silver nitrate. That's sorry, not silver nitrate, zinc nitrate, aqueous zinc nitrate, and silver solid. Okay, and here we have calcium in water, producing calcium hydroxide and hydrogen gas. This would be a gas right there. Here we have magnesium bromide combining with chlorine. That would probably be a gas, chlorine gas, and producing magnesium chloride and bromide. Here we have iron 3 oxide and aluminum reacting to form aluminum oxide and solid iron. And there you go. All right. So the whole lab was all about single displacement reactions and double displacement reactions, so you get a taste of what happens with all of those, and we got a lot of neat practice writing formulas and writing the correct balanced equations for each of these reactions. All right, let me know if you got questions. Keep up the great work, and please submit this so that I can look at your wonderful, wonderful work.